Welcome to Ready to Derive. In this video, we're going to cover applications of related rates as they pertain to distances and length. If you haven't yet watched my video on Introduction to Related Rates, you might want to do that first. I'll link it in the description. In that, I review implicit differentiation, which is essential to this study, and I lay out a four-step process for solving related rates problems. I will review those briefly in the next slide, but you might want to check that out if you need a little more detail. Now, in that first video, I did cover one classic distance problem or changing length, and that was the ladder against the wall. In this very classic but unrealistic setting, you have a ladder leaning against the wall and you start pulling out the base of the ladder, because what else do you have to do? And as you pull out that base, the top of the ladder begins to fall. And something that we're interested in is what is the rate at which that ladder falls, depending on it, like a particular scenario at a certain point in its journey. What journey? Journey down to the ground. In a certain point in that journey, you can calculate the rate at which the height of the ladder is falling, given the rate at which you're pulling the bottom of the ladder out. So fascinating stuff, I hear you say. But anyway, without further ado, let's begin.
So let me first lay out the strategy for solving related rates problems. So the first thing is it's essential if one's not given for you to draw a diagram, and then to make sure you assign a variable to any quantity that varies with time. And so I've abbreviated this step to diagram and variables. The next step is really an organizational step, because these are all word problems. There's lots of numbers and things floating around. So it's really important to lay it all out, organize it, identify any rates of change you're given, except of course for the one you need to find, and any snapshot values. I'll explain that in more detail when we do an actual problem. The third step is to write an equation linking all the variables and then implicitly differentiate. Now, the equation is sometimes given, but sometimes it's not, and that's where the diagram helps, so that you can create the equation. And then the final step, of course, is to substitute all the values that you have sort of outlined in step 2. Substitute all those in and solve for the unknown rate. At that point, you may have to find additional values if they appear in your equation. So let's get started with an actual example. So for our first practice problem, we're going to actually do a classic called the shadow problem. I don't think I've ever come across a calculus textbook that doesn't have one of these problems. So here goes. 6-foot man is walking away from an 18-foot lamppost at a speed of 8 feet per second. How fast is his shadow lengthening when he is 12 feet from the lamppost? So let's look at a diagram. And the variables that we assign. So here we go. Here's the lamppost. And here is a person walking away from that lamppost. And we know, you've probably always done this yourself. It's if you stand right under the lamppost, of course, you have no shadow. And as you walk away, your shadow lengthens. It's kind of like fun to see how long your shadow can get. So I'm sure we've all experienced this before. So let's think about, we're interested in how shadow is lengthening. So we need to kind of give a variable to that shadow. So let's get the last ray of light that escapes past him, because that's where the shadow will end. So if we see that this will be his shadow, right, on the other side of the light, and we have to give that a variable. So I'm just going to call that B. Now, what else is varying? So we have to identify anything that's varying, and there are some things. So for example, that yellow ray is varying, but we're not really interested in that. We're not given any information about that. The hypotenuse of the triangle, in other words. So we don't need that, but he is moving away at a certain speed. So as he moves away and his shadow lengthens, then his distance from the lamppost, we'll call that A, is also lengthening. So the other thing I like to put into the diagram is anything that stays the same and doesn't change as he walks away. So the height of the lamppost is 18, that stays the same. His height is 6, I'll put the 6 there. But what you don't want to do is put that 12 in there. So this 12 here, that's a snapshot value, because that's just at one moment in time. So A is 12. At that moment in time, we would like to know how fast this shadow is lengthening, but don't put that in the diagram because that can get you into trouble because you'll start using it when you shouldn't. And so now we identify the rates of change and also any snapshot value. So he's moving at a speed of 8 feet per second. So that's really how fast A is changing. So I'll put dA by dt equals 8. And at the moment, the snapshot value at which we like to work out the rate is when A is 12. So that's the snapshot value. I'll put that in my organizational table. And then dB by dt is how fast his shadow is lengthening. So that's what we want to find. I'll put a question mark there. And B, I'm not given that. We could find it if we need it, but I would say hold on for, hold out for that until we see if we actually need the value of B at a later step. So moving on. So let's bring up that organizational table and a simplified diagram from before, and we'll label this was 18, 6, this was A, this was B. And it's important to observe that those are right angles there. So now we have to come up with the equation linking A and B. Again, sometimes people see the right angle and they're like, oh, Pythagorean theorem, and they go to find the hypotenuse, but there's no information about the hypotenuse. It's really not helpful. So we need something more directly to link A and B. You have to stretch your mind back to geometry here a little bit and realize that because they both share a right angle, when I say they, the triangles, they share a right angle and they have this angle here in common, we actually have a pair of nested similar triangles. Let me pull them apart to help sort of see what's going on. So we have, this is 18, that's the lamppost, that's the height of the man. The shadow length is B. And this whole length here, the base of this triangle, is actually A plus B. So we have the little right angle where we have a pair of similar triangles. And if you recall, the sides are in proportion. So if I take the height of the lamppost and take that ratio to the height of the man, that 18 is to 6 as A plus B, the leg of the bigger right triangle, is to the corresponding leg of the smaller one. So sorry, the 6's look a bit like B's, but this is a 6, and I'm going to simplify this right now. And then cross multiply. So I'll get 3B equals A plus B. I'll bring the b's to one side. It's good to get the equation as simplified as possible. And since I am solving for dB by dt, I think I'll isolate b and write it like this. At this point, this is the equation, and now we're going to take the derivative of both sides with respect to time. So, and when we do that, we get dB by dt equals 1/2 times dA by dt. So in fact, A and B are just not even involved in this equation. So it's lucky I didn't waste my time trying to find B. And the fact that A equals 12 at that snapshot value is really doesn't make any difference. So now we're at the point where we can substitute and solve. So dB by dt equals 1/2. dA by dt was 8. So we find out that his shadow is lengthening at a constant speed of 4 feet per second. I say constant because obviously it's independent of how far he is from the lamppost because A is not involved. So that is the final answer. But they do often tack on an extra question to this type of shadow problem. And they ask, how fast is the tip of his shadow moving? So that's this point here. So how fast is that moving away from the lamppost? So what we're really looking at is we introduce a new variable, L, call L. So L is just the sum of A and B. And we would like dL by dt. So we have to take the derivative with respect to time of both sides. And we get dL by dt. Oops, sorry, I guess just go to white there. So dL, okay, so it's not being cooperative. There we go. This should work. dL by dt equals dA by dt plus dB by dt, and dA by dt that was given, is 8. dB by dt is 4, so 12 feet per second. is how fast the tip of the shadow is moving. And we have completed the shadow problem. So our next practice problem is also a classic related rates problem. I've made it a little more interesting by using Batman and Robin, but often it'll start like 2 cars are traveling, or 2 trains are traveling, or 2 airplanes. So anyway, the same kind of idea in each case. So first thing is to set up a diagram with variables. So let's see, let's just use some colors here. So we know that, all right, so the Batcave, let's see, pretend the Batcave is here. X marks the spot. And we have Robin going due east. So this is Robin. And we have, let's see, Batman going due north at a certain speed. And I thought Batman, I was going to write that he's flying at 80 kilometers per hour, but in fact I found out he can't fly. He has to kind of use his cape to glide. So he's gliding in that direction, and we have to find the distance between them, how fast the distance is changing. So we need this. And let's call that distance, so we got to give that a variable because it's what we want to find. And we know Robin, we know the speed that he's going at, so I'm going to give him a variable, x, and Batman also y. So notice I really haven't put any numbers into that diagram because I don't want to get trapped into thinking we're at some sort of static position. So now we got the rates of change and snapshot values. So Robin is going, so dx by dt, that's his speed, is 100, and x equals, well, we weren't specifically given that, so we might have to find that. Batman is going at 80, and by the way, usually what I do is I kind of check off, as I organize the information, I check it off in the problem, so I don't have to keep rereading it. Y, and we would like to find dz by dt, that's the unknown, and we may need z, we're not sure. Now, the thing is that I'm telling you ahead of time that we do need those snapshot values. So to find those snapshot values, what you want to do is create a little snapshot triangle so that at that moment in time, after 30 minutes, you know, where is everyone? What is the value of x, y, and z? So x, if it's half an hour, then that means that Robin will have only gone 50 kilometers an hour. Hold on, 50 kilometers. Let me write that there. And then Batman will have gone 40. And we need to find the distance between them at that time, and we'll call that z. So we can just do the Pythagorean theorem. So 40 squared plus 50 squared equals z squared. And if you solve that all out, you'll get that z it's going to come out to a radical, but it's approximately 64. So we can say, so at that moment in time, 30 minutes into the trip, x is 50, y is 40, and z is approximately 64, and we'll bring this information onto the next slide. So let's call up the table, and let's call up the image again, and remember this is x, y, and z. So the equation clearly is going to be the Pythagorean theorem, which is that x squared plus y squared equals z squared. And now that we have the equation, we'll take the derivative of both sides with respect to time. So d by dt, it's a little hard to squash there, z squared. And we would get 2x, by the implicit differentiation, 2x times dx by dt plus 2y times dy by dt equals 2z by dz by dt. And you can sort of see that the 2's are going to cancel, so we can get rid of those. And now, rather than isolate dz by dt, even though that's what we want, it's sort of easier just to kind of substitute in and then solve. Probably likely to make less mistakes this way. So x times dx by dt. So at this moment, x is 50 times the speed, so Robin's speed is 100, plus, and then y dy by dt. So that's 40 times Batman's speed, which is 80, and that has to equal z times dz by dt, which is 64, and that's what we want to solve for, dz by dt. So that would make, let's see, 5,000 plus 3,200. And then we're going to divide by 64 to get dz by dt. And that comes out to be 128.125. And we are in kilometers per hour. So that is the speed at which the distance between them is changing. And I just want to you to observe that if I just put this in the table, so 128, now there's some rounding that's been going on, but I'll leave it like that. You might notice that, in fact, wow, the rate just seems to be double the distance. In fact, we probably could have figured the answer of 128 out without doing any calculus, but then what fun would that have been? And the reason is that, well, speed is distance over time. So if time is the same, so speed equals distance over time, or rate equals distance over time. And if the time is the same for both of them, then it means that speed and distance are proportional. So in this scenario, so this is not always the case, but it was kind of fun to see that there could have been a shortcut, and there is a nice relationship between the values. But the next problem we do, there could be no shortcuts. It can only be done with calculus. So for our third and last practice problem, I don't want to insult it by not calling it a classic, since every other problem I've referred to as a classic problem, but this is a typical problem. Not as classic as the ladder problem or the shadow problem, but here goes. So we have a particle moving along a curve, and we'd like to know how fast the distance of that particle is changing from the origin at that instant. So in terms of the diagram and variables, you really don't have to know what this curve looks like to create the diagram. So it's important to kind of be able, not be intimidated by not knowing what the graph looks like. So let's see if you could just make a generic curve here. And let's get, so what do we have here? Whatever the point is, we know its y coordinate, that's one variable. Let's see, its x coordinate. And just for a different color, we are interested in how fast this distance from the origin is changing. And maybe I should just label, so that point is any generic point, x, y. In terms of, let's quantify those rates of change, if we have any. So we have dx by dt equals 3. So that's taken care of. And that particular, we're interested in when x equals -1. So we got that taken care of. We do not know dy by dt. We may need it, we may not, but we'll just code it there anyway. And so we know that y equals 4 at that moment in time. And we are interested in the rate of change of d with t. So that's really what we're interested in. But we don't know d. And I can guarantee you that we will need to know it. So what we're going to do is find d right now by creating a snapshot triangle. And again, so now I will put this is over here at -1, 4. And so that we know that, let's see, this is 4, x is technically -1, but it's going to become 1, and then we would like to find d, and we can use the Pythagorean theorem. So d squared equals -1 squared plus 4 squared, and that comes out to be 17. So we know that d is the square root of 17. So let's call up the table of values, and we're at step 3 to write the equation and differentiate. So here is the sketch from before, which obviously we are going to be using the Pythagorean theorem. Now, if we took the derivative with respect to time of both sides, we would get dy by dt and dd by dt involved, and that's not going to be helpful because they're both unknowns. So one way would be to find dy by dt another way, and that would be by the equation of the curve. So we could take the derivative with respect to time of both sides and get dy by dt in terms of dx by dt and find it that way. But we can be even more clever. You may notice that we have y squared here, but we also have y squared expressed in terms of x. So why not make a substitution? So instead of y squared here, we're going to put 4 times 3 minus x, and then we've removed the issue of not knowing dy by dt from the table here, and we are ready just to take the derivative with respect to time on both sides. So then we would get 2x dx by dt. Actually, you know what might be good just to distribute here. So this would be plus 12 minus 4x. So the 12 is a constant, the derivative would be 0. And then we'd have minus 4. And don't forget, still x is varying in terms of time, so we must have dx by dt there as well. And then we would get 2d d by dt. Notice that, let's see, the 2, that could cancel out with that 2 and divide into here 2 times. So then we can substitute and solve. So coming down to here, x is -1 and dx by dt is 3. And continuing along, minus 2 times dx by dt again, which is 3, equals rad 17 times the derivative we would like to find, the rate of change we'd like to find. If we just rearrange this, so the left-hand side would simplify to -9, divide through by root 17, and that will come out to -2.18 units per second. So that's interesting. So dx by dt is positive, but d by dt is negative, which must mean it's shrinking. So let's just end with a visual, kind of look at what's going on. And if, so dx by dt is positive, it means that the particle is moving to the right. And then if it's moving to the right, that means that its distance from the origin right here, as it moves closer to the right, it's going to be getting smaller. So that's why it's negative. Thank you for sticking around to the very end. If you enjoyed my content, please don't forget to like the video and subscribe to my channel, Ready to Derive. Thank you.